You ever just look at a tiny little pill and think, how is this thing about to go on a super complex, targeted mission inside my body? I mean, it's kind of mind-blowing when you really think about it. So today, we're going to break down that amazing journey a drug takes, from the moment you swallow it to the moment it makes its exit.
Right, so that's the big question, isn't it? It feels like magic, but it's actually this beautifully precise science. How in the world does a painkiller know to go after your headache and not, your big toe? Let's follow that pill and figure out its secrets.
All right, so the first part of our drug's mission is all about finding the right target. And honestly, the best way to wrap your head around this is with a really simple but brilliant analogy: a lock and a key.
So here's the deal. Your body's cells are covered in millions of these tiny molecular locks. Scientists call them receptors. Now, the drug molecule itself is the key, and it's been designed to fit perfectly into one specific type of lock. When that key slides in and turns, bam, it triggers a response inside the cell. And that right there, that's the therapeutic effect, the very reason you took the medicine to begin with.
But what's really cool is that there are different kinds of these locks. On the one hand, you have your standard cellular receptors. The key fits, and it kicks off this whole chain reaction of signals inside the cell. But then, other drugs work on something called ion channels. You can think of these like tiny gates on the cell's surface. The drug is the key that either opens or closes that gate, basically acting like a doorman, controlling who gets in or out, and changing the cell's whole vibe.
Let's make this super real with an example. Take a beta blocker. Your body naturally makes adrenaline. That's a key that fits into receptors on your heart cells, telling them to speed up. A beta blocker, though, is like a key that's designed to fit that same lock. It gets there first, slides into the keyhole, and then just stays there. It completely blocks it. So now, adrenaline can't get in. And the result? Your heart stays calm. It's so simple, but it's incredibly effective.
Okay, so mission accomplished, right? The drug found its target, it did its thing. But obviously, it can't just hang around in your body forever. And that brings us to the second act of our story, the body's cleanup crew.
So that's the next logical question, right? The drug did what it was supposed to do. Now what? How does the body actually get rid of it? Well, it turns out our bodies have this incredibly sophisticated disposal system built for this exact job.
Turns out, the body has two main strategies for this cleanup, and they work in totally different ways. First, you've got what's called zero-order kinetics. The best analogy for this is a bouncer at a club who only lets, say, 10 people out every hour, no matter how packed the club is. It's a constant, fixed rate. The second strategy, and this is the one most drugs follow, is first-order kinetics. This is way more like a fire drill. The more crowded the building, the faster people pour out of the exits. The rate actually changes depending on how much of the drug is left. Let's dig into zero order for a second. The key word to remember here is amount. Basically, the body's cleanup system, usually enzymes in the liver, gets completely overwhelmed. It's working at max capacity, so it can only process a fixed amount, like, say, exactly 10 milligrams every single hour. It doesn't matter if there are 20 or 200 milligrams in your system, the rate stays the same.
Now, let's compare that to first order, which is how most medicines work. The key word here is fraction, or percentage. Your body removes a constant percentage of whatever drug is left. So maybe it clears out 50% in the first hour. In the next hour, it clears out 50% of what's left, and so on. The cleanup process actually slows down as the drug level drops.
So, we've got the lock and key, we've got the cleanup crew. But what does all this biochemistry actually mean for you in your everyday life? Well, that's what this final section is all about, why the dose matters so much.
Seriously, why should you care about any of this when you're just grabbing a pill from your medicine cabinet? Well, understanding this whole journey is absolutely the key to using medicine safely and effectively. This isn't just some cool science fact. It has huge real-world consequences.
And here's where it all comes together. This science explains your dosing schedule, why you pop a painkiller every 4 hours, but an allergy pill is maybe just once a day. It's all about how fast that cleanup crew works. And this is crucial, it explains risk. For those rare zero-order drugs, like alcohol, the cleanup crew just can't work any faster. Remember that bouncer? He can't speed up. If you take too much, the system gets completely overloaded, and that's why the overdose risk is so much higher. Ultimately, this is the exact knowledge scientists use to design safer and better medicines for all of us.
So, the next time you take a pill, just take a second and remember the incredible journey it's about to start. It's not just a chunk of chemicals, it's a precisely designed key on a mission to find a very specific lock with a carefully timed exit strategy. It's just a remarkable piece of science at work.
It really makes you wonder, what other incredible journeys are happening inside you right now that you've never even thought about?